When object-oriented systems fail, we blame abstraction, patterns, complexity. Every serious object-oriented production bug reduces to this. A write crossed a boundary that shouldn't have allowed it. An object state changed somewhere unexpected. That change persisted. Later behavior depended on it. This isn't about syntax, it's about ownership of memory over time. Today we'll walk through multiple object-oriented failure cases. Each one will follow the same pattern: a boundary, a write, persistent state, unexpected behavior later. Stack frames are temporary. Heap objects persist. When a method writes to a heap object, that change survives after the call ends. A boundary is simply the edge of a method or class, a control point where state ownership shifts. If you mutate inside your boundary, fine. If you mutate across a boundary, you are altering someone else's memory. Every failure case today is just that: a write crossing a boundary without clarity of ownership. The object lives on the heap. GetNext increments ID. That is a write. Now imagine two callers. Caller A invokes it first, gets 1. Caller B invokes it second, gets 2. Swap call order, results change. The method name implies reading. The body mutates. This is semantic boundary violation. You've hidden mutation inside what appears to be observation. Now behavior depends on call sequence. That increases cognitive load and test complexity. Mutation isn't wrong, but hiding it behind a read boundary is. Separate the boundaries. Peak performs a read. No mutation. Increment performs a write. Mutation is explicit. Now call order only matters when calling write methods. You've reduced ambiguity. The rule is simple. Read paths must not mutate heap state. Write paths must clearly signal mutation. Clarity at boundaries stabilizes systems. The caller passes a reference. That reference will point to a heap object. Inside the method, order total changes. The stack frame ends, but the heap object remains mutated. The boundary was crossed. Did the callee own that object? Did it have the right to mutate it? If the caller assumed immutability, you've introduced instability. Silent mutation of shared objects is one of the most common object-oriented failures. The problem isn't syntax. It's unclear ownership of persistent state. Now mutation is controlled. The original object remains untouched. A new heap object is created. The caller decides whether to adopt the new state. Ownership remains clear. Yes, this can cost more memory, but boundary discipline often reduces far more expensive debugging later. Control mutation at the boundary owner. This boundary leaks. Get items returns the internal list. Now any external caller can mutate it. The class has lost control of its own memory. The boundary that should protect the internal state has dissolved. When bugs appear later, you don't know which caller mutated the list. This complexity, yes, it's uncontrolled mutation crossing a boundary. Ownership must be enforced. Now the boundary is restored. The internal list remains private. The caller mutates a copy. Yes, copying has cost. but uncontrolled boundary crossing costs more. When state ownership is clear, system reasoning becomes local again. This one is subtle. The object caches a result. GetReport returns the same heap object every time. Now imagine a caller does this. Service.getReport.clear sections. That mutation affects the cached object. Future callers now receive a corrupted report. The boundary violation isn't during construction. It happens through returned references. The method exposes internal mutable state. Ownership is lost. Caching plus mutability plus reference sharing creates silent system corruption. Common bug in service layer object-oriented programming. Now, ownership is preserved. The cached object stays internal. Either we return a defensive copy or we design the cached object as immutable. Immutability is the strongest boundary. No one can mutate what cannot be written. Caching is not dangerous. Shared mutability caching is. Whenever you return internal references, ask, is this object safe to mutate externally? If not, you've created a boundary leak. First, trace execution and find writes. Second, identify which boundary they cross. Third, define who owns the state. Fourth, restrict mutation to that owner. This method scales across architectures. You don't need new abstractions. You need boundary clarity. Global mutable state removes boundaries entirely. Any method anywhere can mutate it. Ownership disappears. Now behavior depends on global call order. Tests interfere with each other. Debugging becomes systematic. Global mutation is boundary collapse. Now configuration has ownership. Its lifetime is scoped. Mutation is restricted. You can trace writes again. Boundaries restore predictability. Yes, object-oriented programming is about state, but it's about control state. Encapsulation isn't aesthetic, it's mutation control. Objects own state. They must defend it. Exposure without ownership creates instability. Mutation is a right. Side effects are rights that cross boundaries. Stability comes from control ownership of state over time. Every failure we saw, mutating parameters, leaking collections, and the others, all reduced to uncontrolled boundary crossing. Object-oriented design is more than class diagrams. It is about deciding where mutation is allowed, and more importantly, who owns persistent memory.